All right, time to get ready for some limit tests. Here we go. First thing, we got some graphical limits. So as x goes to -3 from the right side, the little plus sign there means the right side. So we're coming to -3 from the right side. That's right here. We're going to about, that's about 0.75. And then whatever that y value is right there, okay? So we have then x goes to -3 from the left side. That means we're coming down here. So we're approaching an x value of -3, and we are at, what, -7.75, I think that is. So -0.75. Then the question is there a limit as x goes to -3? Notice there's no negative or positive here, and there is no limit because these are going to different places. So we have to say that this limit does not exist because we're not going to the same place. To be a limit, we got to be going to the same place. All right. Then x is going to -1. So as x goes to -1 from the left, we're going up to infinity. From the right, it's going up to infinity. They're both going in the same direction, so that's going to infinity. Then x goes to 2. So when x goes to 2, from the left, we're going to -0.5, and the right, we're going to -0.5 also, so that's -0.5. Even though that point isn't actually there, this is not continuous at 2, but it is limit. Now as x goes to -2, from the right, it's going down to 0. From the left, it's going down to 0. So they're both going down to 0, even though they're going in a different kind of way. So since they're both going to the same place, the limit exists. Okay? Finding some limits algebraically here. All right, we're going to -infinity. So when we're going to -infinity, the small numbers don't matter. So when x is at infinity, 9 doesn't matter. When x is at infinity, we got x squared here. So -3x doesn't matter. All the small powers don't matter. Here, when we compare 4 minus x, that's like -x plus 4. And when x is infinity, 4 doesn't matter. Okay? Because x is a gigantic number. Okay? It actually never reaches infinity. So when it's huge, then that 4 doesn't matter. So the limit as x goes to -infinity can be simplified here. 5x squared all over the 2. And this is -x squared. All right? And so this is just x squared, and this is x squared. And so that we're left with this 5/2. All right? Here we're going to 5. So 5, and when you plug in 5, you get 0 in the denominator. So that's a problem. We can't just plug it in. Our goal is to plug it in, but we can't just plug it in. So we have to factor. The top becomes x plus 5. Nope, scratch that. X plus 8 times x minus 5. Okay? And the denominator factors to 2 times x minus 5. This is a removable discontinuity that can be removed. Oh, by the way, this is 5. And so we get the limit as x goes to 5 of x plus 8 all over 2. And let's fix that. Now we can plug 5 in. That's not a problem. So plug in 5, and we get 5 plus 8 over 2, that's 13/2. Okay. And over here, we want to factor by the conjugate, because anytime you have this radical, we want to rationalize the numerator or the denominator, whatever it's in. All right? It's going to go downstairs and become ugly, but we're hoping that this will help clean things up. So we know we have a plus b times a minus b. And so we multiply that out. We get a squared, which is 2 squared, minus b squared, which is the square root of 7 plus x squared. So when we square these two things, the square root's going to go away. And we don't need the middle terms because they drop out. And we're left with x plus 3 times, don't forget your parentheses, square root of 7 plus x. And that's a limit. All right? So we have 4 minus 7, this gets distributed, 4 minus 7 minus x, and that's going to be, still have our limit here, that's going to be a negative 3 minus x all over x plus 3 times 2 plus the square root of 7 plus x. And if you factor out a negative 1 from the top, this is negative 1 times x plus 3, so we get a negative 1. These guys are going to cancel. And we have 2 plus the square root of 7 plus x. Now we can plug that in. And we have negative 1 over 2 plus square root of 7, square root of 4 actually, which is 2. So that's negative 1/5. When we have a compound fraction like this, now we need to simplify this. We need to get a common denominator. So let's do that. Common denominator is 5x, so multiply top and bottom by 5 here. And we get 15 over 5x. Multiply top and bottom by x here. We get x squared plus 8x all over 5x. And the bottom, the whole fraction is going to stay alone. Stay by itself. All right. And simplifying the top, we get x squared plus 8x plus 15 all over 5x. And let's change the bottom to multiply and flip 1 over x plus 5. Multiply by the reciprocal. And so this equals limit as x goes to negative 5. Going to factor the numerator. That's x plus 3 times x plus 5 all over 5x times x plus 5. And the x plus 5 is canceled. Now this is not a problem. We can just substitute the negative 5. And we get negative 5 plus 3. That's negative 2 all over negative 5 times 5, negative 25. So that's 2 25ths. Okay. Now we have sine of 4x all over 3x squared. Okay. So our goal is to end up with the sine of 4x over 4x. Okay. So when we have sine in the mix, we wish this was sine 4x all over 4x. Well, we're allowed to do that as long as we keep our 3x squared around. Got to keep that around. That's part of the problem here. And we want to have this 4x has to match with a 4x that we got to put here. So if you simplify this guy here on the right, it becomes what we started with. Okay? And the reason for doing that is when we find the limit of this part here, we know that that becomes 1. And this stuff over here becomes 4 over 3x. We haven't found the limit of that, so we'll keep that around. All right. So these are equal there. And then last but not least, this equals 1 times 4 over 0. So this guy's going to 0 here. As we get 0 on the bottom, this thing gets huge, okay? So we have 4 divided by 0, or a very small number. 4 divided by a small number is a big number, okay? 4 divided by 0.01, 4 divided by 0.001, so on and so forth. So this thing is growing, and it's going to become infinity. and continuous here, all right? So we want to find the values of c, so this is continuous. Well, that just means that when x is 2, these two things need to have the same value. So x is 2, so 2 squared minus c squared has to be equal to 2 plus c. So notice we only have one variable now. So 4 minus c squared equals 2 plus c. And so we're trying to solve for c here. So this is a quadratic, notice that. Okay, so let's move everything to the right, add c squared. Whoops. And we end up with 0 equals c squared plus c minus 2, which is c plus 2 times c minus 1, right? Okay. So what do we have? We have c equals negative 2 and c equals 1. Those are two solutions there. Those are c values that will make this continuous. All right. So... okay, let's talk about some continuous functions here. And so we want a function where f of 0 is greater than 0. That means it's higher than the x-axis. And f of 2 is less than 0, all right? Now, normally, if this was continuous, we would say that it's got to cross somewhere. But the idea here is that we want to have no zeros. So we're going to break the intermediate value theorem. Well, the only way to break the intermediate value theorem is to have a jump of some sort, okay? Or an infinite discontinuity or a removable discontinuity. So we could do, let's make life easy. Let's just use constant functions, all right? We know f of 2 is the cutoff, all right? And we want everything to the left of 2 to be less than 1, let's see, or less than 0. Got to fix that. So everything to the left, to the left of 2, no, that's fine. Okay, f of 0 is something positive, and f of 2 is something negative. Okay, and we want no zeros in between. So because we have some kind of break, this is continuous, all right? And so this could be some piecewise function. And I don't know, this is 1, maybe this is negative 1. So this is, we're positive 1 when x is less than 2. And we're at negative 1 when x is less than negative 1. Less than 2. Oh, greater than 2. Goodness gracious. All right. So that would work. We could also have some kind of infinite discontinuity. We could have done this. We can make a, well, again, 2 is the problem. All right. So we could use some kind of asymptote. All right, and so this is y equals 1 over x. It's shifted right. So we have 1 over x minus 2. All right, so it's positive over on the left. It's negative over on the right, and there is no 0. So it's not continuous, so it doesn't follow the intermediate value theorem. Okay, so create an equation with the given characteristics here, all right? So we got a removable discontinuity at x equals 3, that's a whole, and a non-removable at x equals negative 7. So that is, a graph will help a whole lot here. Okay, at negative 7, 1, 2, 3, 4, 5, 6, 7, okay? So that's an asymptote. Okay, at negative 7 is an asymptote. And then at 3, 1, 2, 3, there's some kind of hole. Okay, so that's not removable. Okay, something like that. So the key is that we got a function, f of x, And if something is removable, then that's going to be something that can cancel. X minus 3. X minus 3. Something that can't be removed is x plus 7. 7 is always a problem, all right? And so there's your function right there. Okay. So the minus 3's could cancel if we wanted to, and but the plus 7 can't. All right? All right. And now, next one, different problem, different setup. We want f of 0 to be -1, and we want the limit as x goes to 0 to be 3. Well, this means it's not continuous. And so if it's not continuous, the only way to really do this is to do a piecewise function. All right? So we're going to want, when x equals 0, for this to be -1. But we want it to be 3 from everywhere else. So in other words, we got some graph 1, 2, 3, and we're approaching 3 from both sides, but f of 0 really is -1. So let's make a graph like this here, okay? And we can simply just say that's the line. Let's say y equals x plus 3, right? And when that's going to there, this is for all values of x that does not equal 0. And when x is 0, we've got to jump discontinuity. So all we need, there's lots of ways to do this, but we got some equation that goes through 3, and then we'll use that for everything that's not 0, and then -1 is what we've removed it, and we've replaced it. So one more here. Let's evaluate a limit here. So we got to clean this up. We got to simplify it. Let's see what we get here. We get the limit as a goes to 0 of x squared plus 2ax plus a squared. So square that binomial out. And then minus x squared all over a. And we're going to simplify this. And this is going to lead to our our derivative. That's what it's going to lead to. Okay, we have 2ax plus a squared all over a. And so we can factor out an a. This is limit as a goes to 0. We can pull out an a on top, and these a's can cancel. So that leaves us with the limit as a goes to 0 of 2x plus a. So the limit sticks around until we actually compute this. So let's plug 0 into a, and we get 2x. There it is. All right? So remember, 2 big questions, and here's a big bonus for those of you who are watching this video. 2 big questions we have is, one, we had, well, these are the 2 big questions that calculus wants to answer. Calculus answers the tangent problem. All right, the tangent problem, which is we want to take any graph and we want to be able to find a tangent line for any point on that graph. What is the slope of the tangent line specifically? And then the second question was the area under a curve. Remember that? All right, so area under curve is a question that we're going to want to figure out, and that's a question that calculus answers. So that's where we started. So we got the tangent line and the area under curve. Those are the 2 things, all right? And so we use the limits. These were the limit kind of things that we'll need for that to find those, all right? A couple other little more suggestions here. Be ready to graph a piecewise function, all right? So if we say graph, let's say f of x equals x plus 3 for x less than 1, and then let's say x squared for x that's greater than or equal to 1. All right, so be ready to graph that thing. I don't know, what does this look like? 1, 2, 3. Y-intercept of that, slope of 1. So we're going to be something like this. Okay, because 1 is our cutoff here, right? And then we got x squared. And so that's a parabola, which is going to look like this. All right, and there's a jump discontinuity here. So if we ask you some questions like the limit as x goes to 1, negative, that's the limit as we go to the left of f of x. And that would be, as we approach from the left, that would be going to 4, right? Because we're using the first top part. Okay, if it's going for the right, it's going to 1. So be ready for that. We've done a little bit of that, but not a ton, all right? And so that's kind of fun. Oh, crazy like. All right. So hopefully that helps. And be ready. One more thing. You might look back and remember how to do things like this. Find the limit as x goes to 0 of sine of 5x times, let's say, the cotangent. Is that what I want? Yeah, why not? Cotangent of 3x. Okay? Wonder what that is. Okay? You might think about that. And the limits, you also remember this one. Memorize this guy as x goes to 0 of 1 minus cosine of x all over x. That is going to 0. Okay? So you might think about that kind of problem. We can talk about it in class. All right, good luck. Study hard. And be positive, because you guys are working hard and that'll pay off. So don't give up.